Welcome to section 4.4, other types of equations. This section is included in chapter 4 because the techniques of solving quadratics are going to prove helpful in solving these slightly more complicated equations. The first type that we'll be looking at is the radical equation, and that is any equation involving a radical with a variable in the radicand. So for instance, the square root of x plus 1 equals 5 would be one possibility. Now we solve these equations by raising both sides to the power necessary to eliminate the radical. So in this example, we might square both sides. Well, if I square the left-hand side, x plus 1 under the radical being squared, my square and the radical cancel, and squaring 5 will give me 25. So it turns out that x plus 1 is equal to 25. If we solve for x by subtracting 1 from each side, we get x equals 24. Now this process of squaring both sides, raising both sides to a power, introduces the possibility for what's called extraneous solutions. Now what an extraneous solution is a solution to an equation later in the process that is not necessarily a solution to the original equation. So these extraneous solutions are not actually correct answers to the original problem. So in this section, you always, for this type of problem, need to check the answers that you come up with in the original equation. So if we plug 24 back in, the square root of 24 plus 1, that's equal to the square root of 25, and remember we always take the principal square root of a number. The square root of 25 is itself 5. So this one checks out. Let's see another one of that type. So if I said equals negative 5, we would use exactly the same approach. In this section, we always isolate the radical. If there's more than one, you can pick a radical that you want to isolate. In this case, we're good. We already have the square root of x by itself. So I can square both sides. And that leaves me with x on the left and 25 on the right. So we should be done. But by squaring both sides, we have introduced the possibility of extraneous solutions. So I will check x equals 25 in the original statement. So is the square root of 25, well, the square root of 25 is 5, not negative 5. So this is an extraneous solution. It's the only possibility we came up with, and so there are no solutions to this equation. That is a common theme in this section. Whenever we say the square root of something is equal to a negative number, there is no solution. The reason for this is that the square root of any expression is always greater than or equal to 0. Right? If we take the square root of 0, we get 0. If we take the square root of 1, we get 1. If we take the square root of 4, we get 2, and so on. Never going to end up with a negative output on the left. Now, other trouble that we could run into, remember that the domain of the square root is positive numbers. So watch out for attempting to plug in a negative value. When you go to check something, whatever you're plugging in has to be accepted by the square root. So let's look at a slightly more complicated example of this type of problem. So here we have a slightly more complicated radical equation. If you're referring to the notes on page 58, we have our process. We want to isolate the radical. And I can do so in this case by simply subtracting 3 over to the other side. Now the reason that I do this is when I square, or when I raise to a power, I want to raise the radical only to that power. Otherwise I might have to deal with some foiling. I want this by itself. That way the power that I raise to will cancel it out. Alright, well here I have a square root, so I need to square both sides. So if I square root 2x minus 4, and if I square 4, I will cancel the radical and the square and get 2x minus 4 on the left. And if I square 4, I get 16 on the right. At which point I can solve for x. So adding 4 to both sides gives me 2x equals 20. And so it seems that x equals 10. Now we want to check. So going back to our original equation, 3 plus root 2 times 10 minus 4. That's 3 plus root 20 minus 4. In other words, 3 plus the square root of 16. And the square root of 16 we know is positive 4, not negative 4. We always take the principal square root, which is 7. And that's what we were hoping to accomplish. So x equals 10 is a solution. We did not encounter any extraneous solutions in this problem. But you always have to check. As soon as we square both sides, things can get a little bit strange. Okay. Now, if you're following along with the notes, you'll see there in step 1 it says isolate the radical term. If there is only one, isolate it. Otherwise, you may choose a radical to isolate. Let's see an example involving that concept. So here we have a radical equation involving two different radicals. So they are different kinds of radicals, which means I can't combine them. They're not like terms. And I can't, you want to make sure you don't run into this trouble, you can't distribute a radical over a sum or a difference. So a plus b under a radical is not the same as radical a plus radical b. That's a very common error and you don't want to make it. Alright, so I'll follow along with the steps. The first thing I want to do is isolate one of these. And I think it'll be easiest to isolate that guy. I can do that by adding root x minus 5 to both sides. So that gives me root x on the left, and 1 plus root x minus 5 on the right. So now I'm going to eliminate this radical by squaring both sides. And I put emphasis on the word sides. So I need to square the whole expression on the right, 1 plus radical x minus 5. So on the left, my radical and my squaring cancel. However, on the right, things are a little bit more complicated. 1 plus radical 5, or x minus 5 squared is equivalent to 1 plus radical x minus 5 times 1 plus radical x minus 5. So we can view this as the product of binomials, which means we need to FOIL. Alright, so our first term, we would get 1 from the 1's. Then we'll get 1 times radical x minus 5 from the outside terms. From the inside terms, we'll get another radical x minus 5. And from the last terms, we will get radical x minus 5 squared. At which point we can simplify the right-hand side a little bit we have two of the same kind of thing, 1 plus 2 radical x minus 5, and the radical and the square will cancel, giving us x minus 5. Okay. Now as soon as we FOIL and simplify, we see that there is one radical left. Which means we can start over and isolate that radical, root x minus 5. So we dealt with the root x. Now we're going to deal with the root x minus 5. So let's see, we can subtract an x over to the other side. We can add 5, and we can subtract 1. So if we're adding 5 and subtracting 1, we're adding 4. So on the left, we are left, our x's actually cancel, and we're just left with 4 equals 2 radical x minus 5. And I'll go one step further. I'll divide both sides by 2 to get 2 equals radical x minus 5. And now we'll move on to step 2. We'll raise both sides to the power that will clear this radical. In this case, we're going to square both sides. So if we square 2, and if we square radical x minus 5, we get rid of the radical. We're left with x minus 5 on the right, and 4 on the left. And finally, we can solve for x by adding 5, get x equals 9. Alright, so if we come up with this x value, doubly so in this case because we squared both sides twice, we definitely need to check that solution. So on the left-hand side, we have the square root of 9 minus the square root of 9 minus 5. Well, that's 3 minus the square root of 9 minus 5 would be the square root of 4, so 3 minus 2, which is 1. And that checks out. So x equals 9 is our solution. It's the only solution to this equation. And that's how you'll have to handle those, where you encounter more than one radical. And you got to be really careful with the algebra involved. Remember, if you're squaring a binomial like this, you have to FOIL. Squaring 1 plus radical 5 is not the same as squaring 1 and adding the square of radical x minus 5. Now, so far, we've always squared both sides. Let's see an example of a radical equation where squaring isn't exactly what's called for.